Hello there. This talk is about software dependability and developing dependable software. So let me share with you the slides. Um, Dependable systems. This is the sequence of topics I want to talk about briefly. First, dependability properties, then socio-technical systems. These are systems that include the human element and the social element that would impact the dependability of the system you're trying to run. And some of the measures that we can use to increase dependability, like redundancy and diversity. And finally, a little bit about dependable processes, because a dependable software development process will contribute to increasing the dependability of the software that you're trying to produce. Formal methods and dependability is part of this chapter, but I've already spoken about it in the previous lecture, so I will not be doing very much of that today. Okay, now system dependability is really a very important property of software systems. It reflects the degree to which the users trust that system and have confidence that it will operate as the users expect it to operate, and that it will not fail in normal circumstances or under normal use circumstances. Normally, when we talk about dependability, it's sort of a complex or a composite attribute of software. So there isn't like a single measure, but actually it covers a number of related systems attributes, like reliability, which I mentioned a little bit in the last lecture, availability and security, as well as safety and resilience. So note here that we need to consider the effect of system failures, and we need to guard against these because they can have widespread effect on the environment and the user, people, wealth, businesses, continuity of life, etc., etc. Especially that today, almost everything around us has a large or considerable software element in it, from your digital watch to your mobile to your car to the healthcare systems and devices, the energy generation and distribution systems, and so on and so forth. So systems that are not considered to be dependable are unreliable, unsafe, or insecure, and may be rejected by the user. The user may refuse to use them because they cannot trust them. Now, we always have to think about the cost of system failure. Yeah, dependability actions will cost us, of course, but we have to contrast that with the cost of system failures, which can be very, very high, extremely high. Loss of life, or a very large expenditure. So there can be a large economic loss or physical damage, etc., to property, to cities, to infrastructures, and so on. Also, systems that are not dependable may actually cause information loss with a very high cost, consequential cost of recovery loss. If you lose your data, for example, if your database crashes or because of malicious attack, you lose your data, the effect on the business can be really very extreme. Now, causes of failure could be hardware, software, or operational failures, like usage failures resulting of incorrect or erroneous use. So let's look at dependability properties. And dependability, as I said, is a composite attribute of things like availability, which is the ability of the system to deliver service when requested. It's there, it's running. Reliability, the ability of the system to deliver services as specified, so you can actually trust that it will perform as expected, although this also has a different definition depending on to what extent you can actually rely on it being up on time. So there's a probability here. Safety is the ability of the system to operate without catastrophic failure, without injuring or hurting anybody or causing damage to anything or anybody. Security is the ability of the system to protect itself against intrusion or accidental damage or deliberate intrusion that aims to destroy it or harm it. Resilience is the ability of the system to operate under radically different circumstances, largely damaging events, big events. Okay, so here are some definitions for availability. The probability that the system will be up and running and able to deliver useful services to users. Yeah, so probability, would it be up and running? Reliability is the probability of the system that would correctly deliver services as expected. Safety is sort of, cannot say it's a probability, but it's more like a judgment. High, low, medium, etc. So it's more like a judgment on how likely the system might cause damage to people and its environment. This is the sort of calculation I proposed. I mean, there's a number of mathematical measures of reliability. The simplest of them is the mean time between failure. The mean time between failure, i.e., you say a hard disk will operate like 100,000 hours before it breaks. But obviously, when it breaks, it'll take some time to fix it. So the mean time between failures would be the sum of the mean time to failure, the amount of time it takes until it fails, added to it mean time to repair. So if it functions for 90,000 hours and then it takes, say, 10,000 hours just to make the calculation simple to repair, then the mean time between failure is 100,000 hours. Okay. Now, software availability is a probability that the program is operating according to requirements at a given point in time and is defined as this. So it's the mean time to failure, which we've seen here before, divided by mean time to repair, added to it mean time to repair, and we get a ratio of that. It's a percentage that reflects how available it is. I had a question last time about is that difficult to measure for software? Yes, it is difficult to measure in software. I gave an answer then. I'll come back to it later. But let me just look at just straightforward reliability of hardware components. If you assume that we have two servers, for example, or two database servers or two network servers or something like that, and you want to duplicate them to have two duplicate components doing essentially the same thing to increase the system reliability. So what would be the reliability of the composite system that has those two systems running in parallel? And one of the terms that you might want to observe here is sometimes they say, okay, we're going to have two devices that are load sharing and load balancing at the same time. So they are backup to each other, but at the same time, if the load gets too high, the other standby system can jump in and share some of the load. Also, if the load on one system is too high, then it can transfer some of its load to the other server. So if we assume that these two boxes or devices, whatever they are, have identical reliability figures like 90%, so the likelihood is that at any given moment in time, it's 90% that it will be up and running and available for use. Okay, so that means that the probability that both components fail is going to be 1 minus 0.9 squared, because we have two components, yeah? So the probability of only one device failing would be 1 minus 0.9, yeah? That's the probability of failure. So if you have two of them, so the probability of them both failing at the same time, you know that from probability theory, I hope you square them or you multiply the two probabilities together. So if this is the probability that both systems would fail simultaneously, so the probability that both of them would be up and running working is 1 minus that. Therefore, if you do simple calculation, you'd find that the probability that both components work is actually 99%. Yeah, so adding one extra device running simultaneously would increase the reliability figure in this way. I may also want to look up the concept of RAID, RAID, which stands for Redundant Array of Independent Disk. It's pretty standard these days in database servers where you have this kind of setup. There's not much time to explain it here, but you need to observe that it has a number of levels, and each level has its particular definition, which is something I want to look up later on. So typically, we construct reliability diagrams like these to calculate and evaluate the reliability of the system. And on the previous diagram, you saw only two devices running in tandem in redundant mode. So you calculate a percentage of reliability for that. But what if your system also relies on other layers, other sequences of devices that it needs to operate? So the composite reliability of the entire thing is that once you've calculated the reliability of each of these clusters, you multiply them together, and you can see here that the total reliability of the entire cluster here and the entire composite system here is a little bit lower than the reliability of any of these components by itself. Hopefully this is clear. Why? Because for the system to continue to operate, you need all of them to be working at the same time. Therefore, you multiply the probabilities. So security, again, is something you need to know that it affects dependability. Obviously, if the system is not secure or there's a security breach, the system can be unavailable for use or can produce erroneous results, and therefore the user would feel that they cannot depend on it. So whether the intrusion is accidental or deliberate, is still part of the security type or the security element of dependability. Resilience, as I said earlier, it's a measure of how well the system can maintain and tolerate a sort of disruptive or drastic events and continue to function at least in a lowered performance mode or crippled mode, or as we said before, there's something called graceful degradation if things on the outside change so much in a disruptive way. Robustness is a lesser degree of resilience or tolerance to external circumstances, whereby you might give the system erroneous input, but it can still continue to operate. Yeah, so the system, a robust system, is a system that will continue to perform, even though it has been dragged slightly outside its specification domain. So the system, if the system can still function, maybe at a lower rate of performance or less efficiently or something, but if it could still continue to operate outside its spec, then it's a more robust system. It's like saying a table or a chair is very robust, even if it faces or it has to deal with a load that's far greater than what it has been designed to tolerate. And software could be like very high transaction volume that the software was not designed to deal with, slower data connection speeds. Those of you who have Netflix, I think, might observe that it's actually quite good at coping with reduced bandwidth when it's receiving a streaming video. Yeah, even if the link is poor. So this is an example of robustness. Other dependability properties, apart from the 5 I've just mentioned, and additional stuff that you can also take into consideration is something like repairability. Even when a failure occurs or there's a bug that brings the system to a halt, how quickly can you repair it? Yeah, is it easy to repair? And obviously this depends in software on something like we have clear and accurate documentation of how the system works. It's like having a manual for a machine that you wish to repair. If you have an accurate manual, a comprehensive manual that tells you how this thing works, then you like to be able to repair it quicker. Contrast that with the case where you have no documentation whatsoever. You'll have to spend a very long time trying to understand what is going on so that you can actually trace the fault. Maintainability is about modifiability and tweaking the system to do something like different operations, different functions, catering for new requirements, improving the system, porting it to a different environment or platform. Although at some point I must have said that maintainability also include perfective maintenance if there are bugs. Well, so there's an overlap here between corrective maintenance and repairability. Again, in maintainability, you'll need to have a very good and clear structure and design of the software so they can actually affect maintenance activities like adding new functions without disrupting the whole system, without having to redo a lot of it, and therefore taking a very long time. Composability, so that you can actually use elements of the software system to compose or recompose to serve new functions or change use circumstances. Modifiability to, again, suit new data format perhaps, or new database format, as well as protection from error conditions. Remember, one of the attributes for good modular software methods is of good modular design as a result of a modular or an object-oriented method is that there will be a measure of protection. So you're protecting the system from itself. So if one part has a fault or failure, for some reason, this failure, this fault will not propagate to another part of the system and cause an even greater problem. So protection is part of maintainability, because as you know, when you maintain software, you're likely to introduce problems in another part of the system. Obviously, the less you do that, or the less likelihood of you doing that, the better. Error tolerance, I said something about that under robustness. If the system can still cope with erroneous user input, can still be tolerated, and the system can continue to function without crashing, without introducing further errors, then obviously this would add to the dependability property of the software. What do we do for that as software engineers? Well, obviously we have to look for things like validating input, capturing and handling exceptions. Yeah, so there's an error, but still we don't want the error to crash the whole thing. We want to monitor operation conditions such that if an operation condition takes place, an adverse event, we can still cope with it without having to take the system out of function. Right. Now, there are dependencies, obviously, between the dependability attributes. They're not all independent. So, for example, a safe system would, a safer system would be more reliable. Yeah, because no one can break into it, no one can cause it to crash. Therefore, you can continue to use it. So, a dependency between safety and reliability. The system may be unreliable because its data has been corrupted by an external attack. So, yeah, so again, safety, a link between safety and dependability. Denial of service attacks would also tend to render the system unavailable for a period of time at least. If the system is infected with a virus, it may corrupt your files, it may distort the data, and you get invalid or incorrect data that can cause failures elsewhere. So if it's infected by a virus, as you know, you'll not be able to use the system safely or confidently or reliably. So this is something to bear in mind. Okay, I think you can read this by yourselves, but essentially, when we develop the system, we need to be very careful not to introduce errors in the system, following all the verification, validation, and testing activities that you have already been introduced to, as well as, of course, the design paradigm or design methodology that you're following. It may promote internal mechanisms to actually protect the system from succumbing to errors or propagating errors across other parts of the system, reducing its reliability and henceforth its dependability. So design protection, I mentioned these when I was talking to you about one of the features of object-oriented systems, that because of the encapsulation element, all objects are encapsulated behind their interfaces. Yeah, so the interface act like protection fences that would push back any errors from migrating to other parts of the system. We need also to configure the system correctly for its operating environment. So we need to understand its operating environment very well, so that we can sort of take some measures against what if the environment suddenly changes, and therefore the error condition that our system will have to deal with. And maybe we need to build in capabilities for the system to recognize that there's a cyber attack and be able to resist it and block intruders. Also, we need to build in recovery mechanisms like backups and recovery scripts, so that the system can be restored to normal operations as soon as possible after a failure. The thing is, you need to remember that all of these measures cost a lot. Yeah, there's a high cost to these. These will cost you. They don't come for free. So what do you do? Well, let me first say why is the dependability costly? Well, you either have to follow expensive development techniques and tools and use expensive hardware to promote higher dependability in your system, or you also do more testing, more increased testing and validation verification activities, which again costs money. So basically, you can spend an awful lot on a system to make it dependable. So where do you stop? How do you steer your decision in this area? Well, we need to look at a curve like this, that if you're striving for very, very high reliability, the cost can be enormous. Yeah. So what do you do? Well, you need to examine the cost of failure in your system. Is it worth it? You have to almost, quantify the cost of various types of failures, and you need to say, okay, and discuss with the clients and sponsors, okay, because the cost of failure can be extremely high. I need to spend more money on it, on dependability, to make the system more dependable in the case of a lack of dependability, or one of the failures, a failure in one of the areas I just mentioned. Okay. I will also last time about software reliability. Software reliability is a big area of research, has been going on for over 30 years. But let me just very roughly tell you how it's done. Reliability is modeled statistically. Yeah, so there's some stats to help you with that. And what you do is that you estimate the number of the residual bugs in your software. How do you do that? There's a number of techniques. Famous one is that you deliberately insert some bugs in your software. You run your test activities in V&V and see how many of these bugs have been discovered. You calculate the percentage and you estimate how many bugs are still in your software. So then you calculate the likelihood that this software will cause failure. You calculate a likely time to repair, etc., and then you plot the curve that tells you how likely the software is going to be. And there's something called the reliability growth curve. Let me show you how it might look like. This is called the bathtub reliability curve, because it looks like a bathtub. It's sort of curved like that. How does this happen? Well, earlier on in the life of the software, you discover lots of bugs, so you fix them. As time progresses, the error rate decreases because of the maintenance activities, so it improves, the failure rate improves, it goes down. But at the same time, as a result of maintenance activities and modifications and adapting the software for new environment, or adding new functions, etc., they can also be wear out, and this happens definitely with hardware. Yeah, so the failure rate goes in one way, and it goes up in one way, and goes down and up in one way. Add to that a certain constant assumption, or an assumption of constant rate of failure because of random events, then you get this sort of shape. This is a more detailed figure that separates what happens to software to what happens with hardware. Hardware is prone to this, where the rates of error increase quite dramatically. And software, it could look like that, where you have different upgrades and major deliveries of upgraded software. So you end up with more or less constant software. But actually, in most systems, the percentage keeps going up. Again, maybe not as steeply as hardware, where you have software obsolescence, and then you decide to decommission the software and come up with a new version, or rewrite the software altogether. Okay. So you need to sometimes decide that actually it's okay to accept a less trustworthy system, but obviously you have to be straight up with the clients, and you have to explain to them what they're getting. Sometimes say, okay, it's okay to get a system that's less dependable and tolerate the failure cost. Yeah, tolerate the failure cost. Okay, I'll take that. There's a likelihood for a very high cost occurring, but I'm happy to do that because it might even cost me more if I go for a very high dependability, and the cost of failure might not be so catastrophic. So you're taking a bit of a gamble, and instead of say, okay, I'll bear that if it happens, but let's not spend so much money perfecting the software to make it really a very high dependability factor. However, this obviously depends on business and social and political factors. Sometimes you might want to say, okay, well, this is going to affect the reputation of the product badly. I cannot afford this. It will affect me for years to come. It will stick, so I don't want that. So I'm happy to spend more money and effort on it to make it highly dependable to achieve better reputation. So it really depends on the system type. I was talking about a business system where a failure might be tolerated, the cost might not be too high. or is it a safety critical system, as I discussed with you before. Avionics, process control, factories, railway systems. The cost of failure here might be actually quite high, so might strive for a very high level of dependability. Now, something I'd really like you to understand very well is that no software system works in isolation. There's always surrounding factors, and one of them is the social factors around the software. So, software engineering is not an isolated activity, but it's part of broader systems engineering process. Therefore, software systems are not isolated, but they are components of a broader system. And this is essentially the gist of the general systems theory. We have systems that are all surrounded by higher or bigger or outer systems, and they interact and they affect each other. So, for example, the wilderness weather system is part of a broader weather recording and forecasting system that it is affected by. These would include hardware and the software, the forecasting processes, the system users, also the organizations that depend on weather forecasts, etc., external stakeholders. Yeah, so they all interact together. So we have what is called here the socio-technical systems stack. Yeah, the socio-technical systems stack. In the middle here, we have just the software engineering domain where we care about the operating systems. Okay, we might not write them, but we specify them and we have to understand them because we write software to address or to deal with these operating systems. We have the communications and data management, that's our area, the application systems, our area, and then we have to interface with the business process. Maybe model them, but we don't have to maybe redefine them unless you're business systems analyst where you have to do that. Now, the wider layers of the other parts of the stack include things that would go under the umbrella of systems engineering, not just software. So we're looking around the software. We're looking at the organization. We're looking at the operating system more closely. We're looking at the equipment and the hardware. So we look at how the software is going to be used. And systems engineering entails designing a system that would operate effectively inside this kind of stack that contains not just software, but other things. Hardware, operating systems, people who are using it, the host organization that is going to operate it, the business processes that the software has to serve, etc., even society and the agencies in it. Here's a diagram that I've developed that sort of shows you this sort of systemic idea in IV administration. That's intravenous infusions in medical systems. This was a project that was going on at University College London. I participated in called Eclipse to investigate errors in intravenous infusion. And if you actually study the system well, you find that there are many layers that are affecting something as core, or people might think as technical, as errors committed during the intravenous infusion therapy in medical facilities and hospitals. So all of these things actually have impacts on the things like policies that are being followed and applied in the national healthcare system known as the NHS in the UK. Okay, so you need to think contextually, you need to think around your software if you want it to work. You need to be systems, try to get an idea about what systems engineering is and be aware of the links between software engineering and systems engineering. Okay, so these are the layers in the stack. You can read these: equipment, operating system, comms and data management, applications, business processes. Yeah, if your software has to serve a faulty business process, then the overall effect of the entire stack is that it's not going to work, or it might not work. So you need to be careful of that. That's why I said if you're a business analyst, quite often you would be interested in modeling the business processes and maybe help in redesigning them to make them more streamlined and more efficient, so that the overall effect of the whole conglomerate, the whole system, is beneficial and working as is expected. The organization would also include things like the humans who are operating it, people who are using it. There's a term that we use in information systems called human activity system. There's something called a human activity system, people doing things using your software. So sometimes what those people decide to do affects the functionality and the success of your system. So you need to be aware of that. And even while a society where you have regulators and you have laws and regulations that affect and culture that affect how your system is being operated and used. So you need to be aware of the interactions and dependencies between the layers in this stack on other parts of the system. Because what happens on one level can have a ripple effect through the other levels and therefore impact your software system and how it operates. So if you have a change in regulations, that's a societal element, yeah, change in laws can lead to changes in the business processes as well as the application software. Maybe things like the standards you have to comply with when developing your software. Therefore, for dependability, you need to adopt a systems perspective. It's essential to think like that and not just think of the software alone. If we have software failures, we need to capture any errors within the enclosing layers of the socio-technical system stack and not allowed to propagate outside as much as possible. And we need to understand how fulsome failures in adjacent layers to the software can affect failures in operating systems can affect you, can affect the overall dependability of your system. Failures in equipment can do the same as well. Failure in how the system is being used. If you remember at the beginning of the lecture, I said you have something called operational failures. People using the system. So people using the system can actually break it, can cause it to malfunction, and therefore it will affect the dependability of your entire system. Quite often we need to develop software for regulated systems, i.e. have an external regulator, usually governmental, that sort of dictates how your system is going to be certified for use. And if you don't comply, you don't give you a certificate. Obviously, the user cannot employ your system unless it is certified because the regulations in this country require that. For example, in medical systems in the USA, have the FDA, the Federal Drug Administration, which has to approve or certify lots of things from medications to medical devices. In the UK, you have something called MHRA, medical and healthcare regulatory agency. Again, they have to certify lots of systems related to healthcare. And you have obviously certifications related or regulations related to air traffic control systems, nuclear systems, and factory safety and stuff like that. So you need to be aware if your software system is going to fit within a wider system that actually is regulated, and therefore your software has to comply with certain regulatory requirements. Because things like safety and dependability case has to be developed and has to be approved by the regulator. Therefore, critical system development needs to present, to create evidence to convince the regulator that this is a dependable, safe, and secure system. Okay, so we need to be aware of the safety regulations that affect the system that we're developing, what regulations we have to comply with in developing these, and because these regulations apply not just to your software, but to the socio-technical system as a whole, the entire stack. As I said, sometimes you need to get certification for your system. Again, the whole stack, you need to be aware of your role as software engineer there. And normally you need to develop safety cases, if it's safety critical system, quite extensive, describing what failures are possible, what risks are possible, and what sort of countermeasures have you taken, what precautions you have taken so that any malfunction does not result in catastrophic failure. So it can be as expensive to develop such documentations and such extensive cases and arguments for safety and dependability, etc., as it costs to develop the system itself. So the cost can be quite substantial. Obviously, you can stop this video at any moment and take a pause and look at any of the diagrams or slides more carefully, and then you resume playing it. Okay, redundancy and diversity. Obviously, one of the measures that we can follow to increase the dependability of the system is to have redundant and diverse components. What's the difference? Well, in redundancy, you replicate the system, not exactly like an exact match or exact replica, but you develop another component that aims to serve the same function. So you have more than a single version of critical components, so that if one fails, the other one is available as a backup. And you saw that when I showed you this reliability diagram of two servers. So this is an example of redundancy. You have two components doing more or less the same thing. However, as an extra precaution, you might want to diversify. So you have the same functionality in different ways, in different routes. This is similar to what we call in research triangulation, looking at the same data or the same method from multiple angles at the same time, and you cross-check, you verify. So in diversity, you provide the same functionality in different ways, in different components. Yeah, so there's not just similar components, they're built differently. They're developed differently, maybe different software developed by different teams, sitting on different processors with the same specifications, but provided by different manufacturers, different communication channels, chipsets, and stuff like that. So redundant and diverse components obviously should be independent from each other so that failure of one component does not propagate to the other one. Yeah, and they should not ideally be identical, because otherwise you have a common mode failure, like they both fail in the same way because they have been developed in the same way. So for example, components implemented in different programming languages means that a computer fault will not affect all of them in the same way. Yeah, it could be a programming language because of a compiler error, because of an operating system error, whatever. If you do that, then it's less likely that the two components would fail exactly in the same way or at the same time. Okay, so here's a definition. Redundancy is where availability is critical. You need to keep backup servers and switch to these automatically if failure occurs. That's why these two servers, I drew a cross between them and said these two servers can be defined as load balancing, load sharing, as well as being backup to each other. So that one of them will be mirroring the other. If any of them fails, the other one sort of kicks in and takes over. Diversity is you can use it to provide resilience against external attacks because they are implemented or built differently. For example, you can have two servers. One is using Windows and the other one is using Linux as its operating system. Also, we need some diversity and redundancy in the development process itself. Okay, so for example, if we do validation, we don't just do validation and V&V activities in general using just testing, but we also do things like walkthroughs and reviews. Yeah, so it's multiple prongs attack, or multiple ways of providing V&V activities, not just relying on one technique or one approach. Okay, redundant and diverse process activities. So we do it more than once in different ways are important when we do verification and validation. It's like me saying, whenever you produce a design or a deliverable, get someone else, one of the colleagues, to look at it, to review it. Yeah, someone else, another pair of eyes to achieve the walkthroughs, and maybe you want to double up on that as well by showing it to yet somebody else to investigate or to evaluate it. Now, multiple process activities can also complement each other, and we can have cross checks here. Yeah, it's like when you're doing modeling, when you do models for the classes, you cross check them against models of class associations, for example, or against the entity relation diagram to see if all the classes have been implemented and vice versa, something like that. So if you have different process activities, you can actually get them to complement as well as cross-check each other to avoid process errors, i.e. if the process was faulty in one respect, some errors have gone undetected, maybe the other process would pick these up and prevent them before it's too late. But obviously, redundancy and diversity increase complexity. Yeah, it will make the system more complex, have to do more work, and therefore they can actually increase the chances of errors. So it's a balancing act. To what extent can the complexity resulting from redundancy and diversity can increase the chance of errors versus not doing that and just relying on very tightly controlled verification and validation activities. Therefore, some engineers prefer to go for simplicity and carry out extensive verification and validation activities. Actually, I'll add this in. You might have heard of the clean room approach to software development. where you follow formal methods and very tight V&V activities to greatly reduce the probability of any errors being introduced. So this is something they might want to look at and read a little bit about if you have time. Okay, so the Airbus architecture is actually redundant and diverse, but Boeing 777 architecture, FCS architecture, has no software diversity. So here's a couple of diagrams that I want to look at in terms of fault-tolerant architecture. So we've got two redundant components, and we feed the same values to them simultaneously, and we compare, yeah? So as to make sure that no single error would go undetected. And then obviously we, the comparator here would pick up an output value, or report that there's an error if the two do not match. Actually, obviously, if you have one error in one of these, it's difficult to trace which channel is faulty, but at least you know that there is a problem, therefore you start to take action, depending obviously on how critical the domain is, versus this diagram, which actually reflects a simplified view of the Airbus flight control system architecture. We actually have 5 redundant systems, and it's very unlikely that four of these computers would actually fail. More than four computers would fail, leaving you with no redundant systems. So you might want to investigate that a bit more closely and read up about it, and see that actually we can assure a very high level of reliability and dependability for this kind of setup. You can also use the technique known as N-version programming. So you have the same software being developed by different teams of the same specification, common specifications, but different teams working on them, developing very different software, possibly even, as I said earlier, different programming languages, and we keep comparing the results. Sometimes you have a voting system. Yeah, if you have an odd number, then you can single out the one that has an error, and the fault manager here could actually try to repair some of the errors if it has proper diagnostics and maybe restart one of the systems, etc. But at least we need to be aware that there is a problem, and as I said, if all systems are working and the result is critical, you can actually do a voting kind of arrangement by this output selector, which obviously see which is the more common value or the more common output that is being generated. Therefore, it will produce an agreed result. So the likelihood of a failure as a result of one of them, I'm not talking about just failure as in stopping, but also failure as in producing the wrong output. You may have heard that in space missions, you have at least five different clocks, real-time clocks, and you have a voting system. So if any clock of them goes astray, more than one, even if more than one goes astray, there would be a more common value, and the value would be selected from the other operating clocks. Okay, last thing I want to mention briefly is dependable processes. Now, dependable software critically relies on dependable processes. That's why in software engineering, we have to follow a well-documented process and a well-documented methodology. We can't just leave every software engineering team do things in its own way as much, or in the way that it prefers to do it. So to ensure a minimal number of software faults, it's important to define your software development process very well. It needs to be well defined, it needs to be repeatable, so that if two different teams develop exactly the same software under the same circumstance and the same environment, the software needs to be more or less exactly the same. That's the idea of a repeatable software process. We want to check the concept of capability maturity model. Yeah, there's two versions. There's CMM, capability maturity model, and there's capability maturity model integration that puts together a number of capability maturity model, and that addresses software development capability. It was developed by the Software Engineering Institute at the Carnegie Mellon University. It's a description of how well your process is being documented and managed and monitored and developed, etc. So it reflects the degree of faith and confidence people can have in the software development process for the product. Okay. Now, in case of a legal dispute or a professional dispute, regulators can use information, documented information about the process to check to see if proper software engineering process has been followed or applied. Yeah, they say sometimes the term the state of the art process or professional standards have been applied properly in case you have a fault that leads to losses and the client party wish to sue you for damages, for example, then there will be legal issue here and you need to demonstrate that you followed proper software process, hence me advocating the concept of a logbook or a professional record that documents what activities have you followed to make sure that software is dependable. So all the verification and validation activities will be properly documented, all the test cases, all the test runs will be properly documented. I need to show that you followed the proper process or the due process. Okay, here's just a quick picture of how the maturity model looks, capability maturity model and the levels. You can sort of look that up later, but it's essentially like, okay, you can have an initial level, which is sort of like haphazard, anything goes really. Then managed, you characterize the process and you define, sort of document it properly and can describe it. Then you properly define it in a proactive way, and you manage it quantitatively, and then you optimize it to improve it, and so on and so forth. Okay. So I'll leave you to read the definitions of these in this deck, which I would have uploaded by the time you're looking at this video. Some of the dependable process activities is stuff that we've discussed before during this course. You need to do reviews of everything, especially requirements. You need to check that the requirements are, as far as you can tell, complete and consistent. You need to manage requirements in case they change, and they will change. You need to manage that change properly so that you don't get into a mess. You don't get into implementing, for example, the wrong requirements or matching the wrong requirement to other requirements it's not matched with. So you get an erroneous system in some way. You can also apply formal specifications, which I discussed previously, where a mathematical model of the software is created and formally rigorously analyzed to check its properties. And you can also do system modeling, where you constantly develop models that explicitly define and document how the software is going to be produced. And usually these are graphical models that connect requirements to the design, so you can actually tell that this design actually realizes these requirements that you've agreed with your clients. So the idea of developing explicit models is really important for traceability. You need to trace back the design of the requirements, and you need to trace the requirements forward as well to see where the requirements have been implemented when you come to claim that you've actually completed the development and you need to hand over the system. Okay, other dependable process activities, things like design and program inspections and reviews, static analysis for the software and the models, where you carry out automated checks on the source code of the program, and some smart tools that also check and analyze your graphical models if they are aware of the syntax of the modeling language you're using, like UML. You need to be very careful with test planning and management, where you develop a comprehensive set of system tests and document the results of these as well. Now, dependable processes and agility. Now, to develop dependable software, we often require certification, yeah, so that both the process and the product are documented. And as you know, that goes against the grain a little bit of agility and agile methods. Agile methods are not rejecting documentation, but they put lesser emphasis on documentation. Also important for dependable systems is we have upfront requirements. Yeah, almost complete or as comprehensive as you can get them. So you have upfront requirements, and you analyze these requirements to make sure that the requirements are not conflicting in any way, or in a way that compromise the safety and the security of the system. So this goes against the grain of agile methods, where you are co-developing the requirements as well as the software at the same time. Yeah, so you're doing the system, and you're sort of hacking away at the requirements as well, because the general approach in agile is that you're co-developing the requirements and the system and software as well, and minimizing the documentation. You can see the conflict there. That's why I said in agile approaches, they're not really ideal for developing safety critical systems or very large systems. However, you can still define an agile process that incorporates techniques that emphasize quality and some dependability properties like testing and verification, validation, etc. So maybe you can do a little bit of a compromise, redefining or tweaking your agile process a little bit, and getting your teams to follow a proper and well-documented process, and to plan the documentation and to plan the process in a more sort of careful, or more rigid or inflexible way. Well, you have to do this if you insist on doing following an agile process to develop dependable systems. So really, essentially, following a pure agile process is somewhat impractical for dependable systems engineering. So I'll leave you with this thought, and we'll meet in class soon, inshallah. But at the end of this slide deck, there's a few key points that you might want to look at as a summary of this whole dependable system development. As I said, I've skipped the formal methods part, because I did that as part of the formal methods lecture. So I need to look at this, and you can pause the video obviously at any time to read these slides at your leisure. Finally, here's a little bit of further reading from the main textbook. I've sort of picked up bits and pieces from chapters 10, 11, and 12. The content is largely from chapter 10, with some slides from chapter 11. Chapter 12 is dedicated completely to safety critical systems, with a lot of stuff on hazard and risk analysis. So you might want to look at that if you're interested. There's also a paper here that I've contributed to that discusses the role of the human factor in raising the resilience of infusion devices and intravenous therapy. Okay, so thank you for listening. If you've held up so far, I'm sorry that this went on a bit longer than I wanted it to. I'll see you in class, inshallah. Look after yourself and be safe.